Hello everyone. During the previous learning process, we have acquired a great deal of knowledge about machine learning. So in this section of the video, we will learn many common machine learning algorithms. There is a lot of content. We will make 2 short videos to introduce it to everyone. First, let's take a look at an overview of machine learning algorithms. In the previous machine learning algorithm classification, we know it can be divided into supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. It's not about missing out on semi-supervised learning and reinforcement learning here, but because they are not particularly common. So in this section, we will discuss common algorithms related to supervised learning and unsupervised learning. Let me introduce everyone. We can see there are also a lot of algorithms here. In supervised learning, there are classification problems, regression problems. Under the classification problem, there are many algorithms. There are also many algorithms under the topic of regression issues. The most common ones we may encounter are logistic regression and linear regression. There are also SVM, decision trees, and so on. Of course, they have many algorithms that can be used for classification, can do regression again. Moving on to unsupervised learning, there are clustering tasks and some other types of tasks. In clustering, the most common one we see is k-means. There are hierarchical clustering, density clustering, and even spectral clustering. Other algorithms, such as PCA, it is simply an algorithm for dimensionality reduction. And our Gaussian mixture model, when performing some speech processing tasks, this kind of model is commonly used. So, next we will focus on the relatively simple algorithms in it. Let me introduce everyone. First, let's talk about linear regression. I believe in every course that teaches machine learning. It will all start with linear regression because it is the most basic, the simplest, one of the most practical and common machine learning algorithms. Then linear regression, it is the use of regression analysis in mathematical statistics to determine the relationship of interdependence between 2 or more variables. Simply put, it is to find such a straight line. Of course, in the high-dimensional space, it may be a plane. In the 2-dimensional space, it is just a straight line. Fit the existing data distribution. You don't need to worry about whether it can be fully completed, perfectly fit your data distribution, but linear regression, simply using a line or a surface, fit your data distribution. This page displays a mathematical formula for our linear regression. Right here, add W to X, the most basic mathematical formula. W represents weight, B represents bias, X is the feature of the sample input. It's just that simple. How to obtain such a linear regression model? Right here, we use such a loss function. We still remember the loss function we talked about in our last video. Is the stochastic gradient descent used for fitting? Here is where this loss function is utilized. Minimize its loss function value. We can obtain our best linear regression model. Here, as long as the loss value is minimized, you can get the best model. For linear regression, we have an extended content. It is polynomial regression. One can find a clue from the mathematical formulas. Traditional linear regression is adding this item to that item. Polynomial linear regression has this additional term, this item and this item. In the middle, it represents a lot of this L, represents a lot of expressions. Polynomial linear regression. Its biggest feature is the presence of this x to the power of n term. By looking at the picture on the right, we can see what the differences are between polynomial regression and our traditional linear regression. When it is to the power of 5, we look at this green line. Does it have a strong sense of fluctuation? Is it very curved? After joining the subdirection, it will significantly enhance our linear regression with a nonlinearity. Here, it can be well manifested in nonlinearity. So, this is polynomial linear regression. So, this is polynomial linear regression, one of its improvements. But polynomial linear regression, the relationship between its weight parameters W is still linear. So, it is an extension of linear regression. It is an extension of linear regression. For what? in order to supplement the original linear regression model. Those states when obvious underfitting occurs. So just use polynomial linear regression because it has a better nonlinearity. How to prevent overfitting in linear regression. Sometimes your data may be very linear. The sample you provided is very linear. It will be prone to overfitting. How to solve this overfitting problem. As we mentioned in our previous videos, so here will be a more accurate introduction. We can add a regularization term. For example, this part and this part, above is an L2 regularization term. Here is an L1 regularization below. L2 regularization, we call it ridge regression. L1 regularization, call it lasso regression. Added L2 regularization, you can also review the previous videos. With L1 regularization, we are equivalent to certain features from before, performed an enhancement and inhibition. Everyone can understand. Is this the way? Because the parameter here is W, we are equivalent to some features, performed an enhancement and inhibition. It has achieved such an effect. In other words, we have selected some features, using only a portion of features to complete the fitting, so it can play a role in preventing overfitting. Okay, that's the end of the basic linear regression. Let's take a look at logistic regression. This is a mathematical formula for logistic regression. Logistic regression, it is a classification model, solve classification problems. It has intricate connections with linear regression. In other words, it is based on linear regression, made a change. What kind of change has been made? With the addition of this sigmoid activation function, this is an activation function. To be precise, what should the equation of this activation function look like? It should be this one, 1 plus e to the power of x divided by 1 plus x. Or the following equation below, it is 1 plus e to the power of x divided by 1. But here, we need to switch this x to linear regression, wx plus b. Have you obtained this equation? It's about logistic regression. Okay, so we have learned about logistic regression. After a relationship with linear regression, let's take another look. What is the loss function of logistic regression? Here, it's the loss function of logistic regression. It may be more complicated. However, we need to understand one thing. One thing to remember is, we want to obtain the optimal value of logistic regression. We are going to use this loss function for calculation. So what method should we use? Calculated using maximum likelihood estimation. Then the question here will be, why has this become the largest natural estimate here? Everyone can take a look. What does the y in front represent? Y represents your true value. So your actual value is nothing but 1 or 0. Everyone may have forgotten. Let's take a look at the front. Here, it's nothing but 1 or 0. The processing result after passing through the sigmoid activation function, it's just 1 or 0. So that means this part may be taken. This part may also be taken. The result it obtains, it's just a matter of what your actual value is. And how much is the difference between your actual value and your predicted value? Why isn't this being used? Because the actual value you get is a value close to 1. So at this time, we need to find out one of its maximum possibilities. Perform a calculation using maximum likelihood estimation. So it also says here. Similarly, you can use gradient descent to find all its values of w. Why can it be like this? Find the lowest point and the highest point. Isn't it just a reverse process? Can we also find its gradient direction? Next, let's look at an extension of logistic regression. When it comes to logistic regression, we all know it's a binary classification problem. Can it be extended to multi-classification? Sigmoid function. We all know it will perform a binary classification between 0 and 1. Map your original linear line to this middle. Perhaps a point was located here from this linear line. All points higher than that point are classified as one category. Those below this point are classified into another category. This completes a binary classification. How to map it to a multi-classification problem? Multi-class classification problem. We usually use this softmax function. Just like this, we can have the grapes, orange, apple, bananas are all classified. How was it done? Let's continue to look. Softmax regression. Or, to put it another way, this function, it is the generalization of logistic regression. Applicable to K-classification problems, can be extended to K-classifications, multiclass. It compresses a K-dimensional arbitrary real number vector, or map it to a K-dimensional real number vector. Each element in the vector is limited to a value between 0 and 1. This is one of its equations, a complex mathematical equation. However, we need to pay attention to one point. Its denominator is from 1 to k. Then the accumulation of this function. Above is this function. At this point, I wonder if any of you have a clue. Let's move on to the next one. After looking at this picture, I believe that everyone will have a deeper understanding of the complex mathematical formula just now. This is a mathematical function. Although this is a number, but they are all calculated through a mathematical function. So, the equation just now is easily explained. What is the sum of them? It equals 1, right? So, isn't it 1 divided by 0.09? 0.22 divided by 1. In other words, how does softmax work? We have such a variety of outputs. Output value. It might start as 2, 3, 4, 1. It doesn't matter. I add them up as a total. This is a 10. The probability of the first type is 2 out of 10, 1/3, 4 out of 10, and 1/10. This is the working mechanism of softmax. Of course, this is the simplest example. The specific calculation process should apply the formula on the previous page film. Just through such a simple example here, introducing how the softmax function works to everyone. Next, let's look at the third algorithm in this section. It's the decision tree algorithm. The decision tree algorithm is a milestone algorithm in machine learning. Very important. It is an algorithm based on a tree structure. Each of its non-leaf nodes represents a test on a feature attribute. Actually, this node is a feature. This node may represent a feature of this child. This node is called the squeak feature. This node represents the feature of the neck. So at this node, you are going to test this node to conduct classification, satisfying certain characteristic properties. You can start branching for him. Go to the next node for output. Here, I believe everyone has a rough idea about decision trees. So, classifying branches by branches, until reaching the leaf node, so store the leaf node as the decision result. You can see it here. Short in stature, but it won't squeak. That might be a squirrel. If it squeaks, it's a mouse. Then you see that all these leaf nodes have been assigned to a fixed category. Previously, it was features. The final leaf node is for classification. That's how the decision tree is completed. Branch on each feature, branch all the way to the end. One possible outcome for us. This completes a decision tree. So this is the structure of the entire decision tree. The three parts are the most important. There is only one root node at the top, so each child node represents many features. The final result, represented by all leaf nodes, represents a result, classification result. So what is a key point in building decision trees? Let's take a look at this photo. We just said, to classify at the node, child node, and root node. How do? I classify then? I can't just come up with an idea out of the blue, then he should classify it. It is to classify based on information entropy and Gini coefficient. So, in the definition above, he is talking about comparing the purity of all partitioning operation results. This purity, we usually use this information entropy and Gini coefficient. To serve as a quantitative indicator for him, here is one of his formulas. Formulas for information entropy and Gini coefficient. Everyone can take a look. The P, K in the middle, represents the probability of belonging to this category. The greater the difference in purity before and after segmentation, the better the decision tree. What does this represent? Information entropy, whether it's the Gini coefficient or not, whether it's purity or not, he is always expanding. Or, the more complex the samples in this category you have, more chaotic, the larger this value is. If you have classified one category, among this category, only one kind, sample. At this time, his Gini coefficient will be very small. So we understand now, if I were to classify beforehand, his Gini coefficient is very high. After classification, his Gini coefficient is very small, or his information entropy is very small, so our decision tree is very successful. In other words, from the original messy sample, split into a very clear sample. As a result, my information entropy and Gini coefficient will decrease, so the decision tree I build will be very good. So why are there multiple different quantification indicators of this purity here? Because we have a variety of different algorithms, each algorithm adopts different metrics. Next, let's take a look at the construction process of the decision tree. First is feature selection. From the features in the training data, select a feature as the current node, then evaluate the criteria based on the selected features. Recursively generate child nodes from top to bottom. After confirming the first node, I divide according to the first node, possibly 2 types. It could also be type 3. After the division, I'm using this node again, or is it that this feature has been exhausted, isn't it? I remove this feature from the data set. Using the remaining data set, that is, subset, go back and find him to see based on which feature. This subset is divided based on which feature. Based on which feature is this subset divided? Of course, it could all be binary. It could also be a multi-branch number. Building step by step like this, then the construction of the entire decision tree is completed. There will be a pruning process in the middle because you divided it too finely. Some students may wonder, can I upload my entire decision tree when I finally divided it, he had a sample? In this way, are you directly overfitting? Just think about it. If each of your leaf nodes has only one sample, that's overfitting, isn't it? At this time, pruning is actually needed to reduce its structure. He has both pre-pruning and post-pruning. Pre-pruning is, when you generate this node, I'm about to make a judgment. Do you want to generate it? So post-pruning is based on the final generated result. I'll go check again. I want to take a look at which ones. Merge them together, like this. Now let's look at a small case of a decision tree. Very simple. In our dataset, we only have 3 features: refund, status, and this taxable income. Finally, it will be judged whether you will cheat, cheating, deceiving, so we will classify them based on their different characteristics. Occupying a size of information entropy and Gini coefficient. We went to conduct a branch. Some leaf nodes finally branched too. What conditions do you need to meet? You indeed have the possibility to cheat. Of course, this is just a very simple example. He has only 3 features. In real projects, he may have more features, more complex features. You may end up generating a very large decision tree. These are the first 3 machine learning algorithms we are going to explain. In the next video, we will continue to explain common machine learning algorithms. Goodbye.